This is video 2. We present here the definitions, notations and basic properties of paths. A path is a specific kind of graph. Thus all the paths that we represent here are subgraphs of the grid graph. Nevertheless, we consider here directed paths. A directed path P is a sequence of positions. For any index I of the sequence, there exists an edge of the grid which starts in Pi and ends in Pi plus 1. In this example, the path P is finite and its size is made of 27 positions. In this case, the first position of the sequence is called P1 and has no predecessor, and the last position of P has no successor. All other positions have a predecessor and a successor in P. The direction of a finite path is the vector which starts at position P1 and ends in the last position of the sequence P. We denote the direction of a finite path by V. Thus by definition the translation of P1 by V is the last position of P. Sometimes in a proof when we consider a path we need to remember several specific indices. We represent these indices by the notation I subscript 1, I subscript 2, I subscript 3, etc. Since a path is also a graph, all notations used for a graph can also be used for a path. For example, xpi1 represents the abscissa of position pi1. Here is the path P' obtained by switching the direction of all the edges in P. We say that P' is obtained by switching the direction of P. Until now, we have considered a finite path. Nevertheless, along the proof we will consider three kinds of paths: finite paths, infinite paths and infinite paths. Now, we present infinite paths. This example represents an infinite path Q. Such a path is made of an infinite sequence of positions, but the first position does not have a predecessor. This position is denoted by Q0. In this example the positions of Q are indexed from 0 into infinity. By switching the direction of Q, we obtain the following path. The positions of path Q' are indexed from 0 to minus infinity. Finally, we present here a B-infinite path R. In this case, there exists no starting position. For all integer I, Ri is a position with a predecessor and a successor. Here is a B-infinite path R' with the opposite direction of R but with another position as R'0. Let's go back to the B-infinite path R. Now, we say that a path is simple if and only if it does not contain a loop. In other words, for any indices I and j, if Ri and Rj are the same position then I is equal to j. Except for some few cases, almost all the paths considered in this article are simple. Sometimes we will need to focus on a specific part of a path. Then, we extract a subsequence from this path. This subsequence is called a segment of the original path. In this example, we represent the B-infinite path R in white. In hatched we represent the segment of R from 7 to 33. This sequence of positions of length 27 starts in R7 and ends in R33. This sequence is the finite path P introduced earlier in this video. Consider this finite path P and another path P' such that the last position of P is the first position of P'. The concatenation of P and P' is the following path. The concatenation of P and P' is obtained by merging their common position and adding the sequence P' at the end of the sequence P. The size of the obtained path is the size of P plus the size of P' minus 1. Since the common vertex is not duplicated, we have two remarks about the concatenation operation. First, the concatenation can be seen as the union of the two paths. The main difference is that the union of two paths is not necessarily a path, whereas the concatenation of two paths is always a path. Secondly, remark that the concatenation of two simple paths is not always simple. Consider now the path P and a path P second where the last position of P is the last position of P second. In this case, we start by switching the direction of P second and we concatenate the two paths. In this example, we still consider the path P but we consider a path P second which is obtained by switching the direction of P'. Here is the concatenation of P and P second. This path is the same that the concatenation of P and P prime. Note that the concatenation operation is not commutative. The concatenation of P second and P would have produced the path with the opposite direction. Now we still consider the finite path P. We remind that V is the direction of P. We are interested in the translation of P by the vector V. Here is the translation of path P by the vector V. Remark that, by definition of vector V, the last position of P is the first position of the translation of P by V. Then it is possible to do the concatenation of P and its translation. Here is the result of this concatenation. We obtain a path of direction 2V. Now we are interested in the translation of P by 2V. And here is the translation of P by 2V. And here is the concatenation of these three paths. The direction of the current path is 3V. By iterating this reasoning, we obtain an infinite path called P plus omega. This path is called an extension of P. There exists for other kinds of extension of P. Here is the extension P star plus omega. This infinite path is obtained by concatenating the translation of P by kV with k greater or equal to 1. P is not a subpath of this infinite path. Here is the extension P minus omega. This infinite path is obtained by concatenating the translation of P by minus kV with k greater or equal to 0. Here is the extension P star minus omega. This infinite path is obtained by concatenating the translation of P by minus kV with k greater or equal to 1. P is not a subpath of this infinite path. Finally, here is the extension P omega. This path is B infinite and is obtained by concatenating all the different translations of P by kV. Note that all the extensions of P are periodic. In other words, for any index I, the translation P omega I by V is the position P omega I plus the size of P minus 1. Now, we remind that all the extensions of P are obtained by concatenation and that the concatenation of two simple paths is not necessarily simple. In our example, the path P and its extension are all simple. Nevertheless, it is possible for the extensions of a simple path to not be simple. To deal with this problem, we introduce the following notion. A finite path P is good if and only if the last position of P is the only common position between P and its translation by V. Then all the extensions of a finite good path are simple. This result was published before in the article 1 titled To Rule Them All.